All right, this is part 3 of Notes H. We're going to be doing a little bit of back and forth on this set of notes between our slides and the Desmos graphing calculator. Okay, so we're looking at transformations here, which means we're going to be shifting our graphs left and right, up and down. We can also stretch and shrink them. We can also flip them over the XY axis and origin. So we're just moving things around here. All right, so remember I mentioned that it's important to know your parent functions. In order to demonstrate these transformations, we are going to default to that parent function f of x equals the square root of x, our square root parent function. But realize that these transformations we're doing together apply to any of those parent functions. They apply to any graph. We're just demonstrating them here with our square root function. All right, so in this first example, we are going to graph f of x plus 2. So that means we are looking at the square root of x plus 2. My f of x is the square root of x, and then we're adding 2 to that. Notice my plus 2 is outside of that square root, not inside. All right, so I have this set up for us. Over in our Desmos calculator. Let's see if we can switch over there. Here we go. All right, so right now I have for us graphed that parent function, y equals the square root of x, just like was in our slide. And I am going to add to that, in blue, the square root of x plus 2. Notice what happened here in our graph. That graph moved up 2. So when we're looking at f of x plus 2, the square root of x plus 2, it takes that original parent function graph and it moves it up 2. This becomes so important because if we know what the parent function graph looks like, then we know, oh, it's the same as my parent function, but I just have to move it up 2. Okay. Now, if we peek back at our next example, we are looking at graphing f of the quantity x plus 2 in parentheses there. So, still sticking with that same parent function, f of x equals the square root of x. They've got that graphed for us there in red. But we are going to take that function, and our input is now going to be x plus 2. So in place of x, we are putting x plus 2, which means that x plus 2 is completely underneath that square root. All right, so when we go back to our graphing calculator, and we have y equals the square root of x plus 2, with that x plus 2 underneath the square root, it takes that parent function, we love and know, and it moves the entire graph to the left 2. So when you're graphing this function, try to use some points kind of as references. That point 0, 0 that moved left 2 is now the point negative 2, 0. Okay. You might also want to think about that point 4, 2. If I move that to the left 2, what was 4, 2, when I move it to the left 2 becomes 2, 2. Like a ballerina, 2, 2. So, as we graph these transformations, feel free to use points that are easy to pick out on your parent function to use as reference points to graph your transformation. So that graph in green here, that goes to the points negative 2, 0 and 2, 2 is our new graph that has been moved to the left 2. All right, in our next example, we want to look at f of x minus 2. See if you have any guesses at what's going to happen with this one based on what we just did. So if f of x plus 2 moved it to the left 2, what do you think f of x minus 2 is going to do to my parent function? If you guess that it's going to move it to the right 2, thumbs up. So we are looking at taking our parent function, the square root of x, and we are looking at now the function, the square root of x minus 2, with that entire x minus 2 underneath my square root. It is going to move to the right 2. Here we go. Voila. So again, use some reference points for yourself. If you know your parent function goes through 0, 0, and you need to move your whole graph to the right 2, your new transformed graph is going to be at 2, 0. Use that point for 2 again. You know that point moved to the right 2, so it's now going to be at the point 6, 2. All right, now this time, notice that the 2 is in the very front. So we are looking at 2 f of x. We're looking at 2 square root of x. Again, still starting with that same parent function, but this time we're going to take and multiply by 2. We are going to stretch this graph vertically by a factor of 2. So check out what this looks like. Two square root of x takes my parent function and it stretches it vertically. Now think about what's happening here. That point 0, 0, if I stretch 0, 0 by a factor of 2, guess what? 0 times anything is 0. It is staying at 0, 0. But if I use that reference point for 2, and I stretch it up by a factor of 2, we're now looking at the point 4, 4. So it's that y value that gets multiplied by 2 there. My x coordinate stayed the same. Lots of back and forth on this one. Sorry, stick with me. I wanted to make sure that I could visually represent this for you as well. All right, now think about what's going to happen here. Make a guess for me. 2f of x stretched it vertically by a factor of 2. What do you think 1/2 f of x is going to do? So we're looking at 1/2 square root of x. Instead of stretching it vertically by a factor of 2, we're going to shrink or compress this vertically by a factor of 2. So it's going to shrink it. Use those reference points again. Both of these are in red. This one that I'm highlighting for you is my original parent function. 0, 0 stays 0, 0. That 0.42 though, if I compress it, notice it's now at 4, 1. Half of 2 is 1. It compresses it by a factor of 2. All right. Now, this time we have negative f of x, or the opposite of f of x. We're looking at the opposite of the square root of x, or negative square root of x. I personally love to think back to another parent function on this one, which is x squared. I think a lot of us somewhere along the line have had put in our minds that this is a parabola that opens up because it's positive x squared, and this is a parabola that opens down because it's negative x squared. Okay. What's happening there, though, is that negative in the front is flipping it down over the x-axis. It's reflecting it down over the x-axis. So, same exact thing's going to happen here. We're just doing it with the square root of x function. Okay? So when that negative is in the very front there, negative square root of x, we are going to flip it down over the x-axis there. It's that reflection. Voila. There we go. And again, use those reference points to your advantage. 0, 0, if I flip it over the x-axis, it stays 0, 0. 4, 2, if I flip it over that x-axis, it's going to become 4, negative 2. So it's that blue graph there that is our transformation graph. All right, so that negative in the very front, flipped it over the x-axis, what do you think the negative inside my set of parentheses is going to do? So this would be the square root of negative x. You got it. It flips it over the y-axis. Okay. I secretly love drawing this one because it brings me back to the days of drawing seagulls as a kindergartner. Anybody else used to draw seagulls kind of like this when they were young? So it's that green graph there that is my transformation graph, square root of negative x. Highlighted in yellow, I've got my original parent function. Use those reference points again. 0, 0, reflected over the y-axis, it's not going anywhere. 4, 2, reflected over that y-axis, it is going to negative 4, 2. All right, now, I just showed you a lot of individual transformations there individually, but realize that all of these can be combined with one another, okay? So in this last example I have in this section I want to do with you, we are going to look at transforming our parent function square root of x, and we want to graph negative f of the quantity x minus 1 plus 3. So think about what's happening here. This negative in the very front is going to flip my parent function over the x-axis. This x minus 1 inside the parentheses is going to move my parent function to the right one. And this plus 3 that's outside of those parentheses tacked on to the very end there is going to move my parent function up 3. So we're combining 3 different transformations into one. And again, this is why it becomes so important to know your parent functions. Because if you know what your basic parent function looks like, and you know these generic moves, we can create just about any graph we want from that. Okay, so check out what this looks like once I flip it over the x-axis, move it right 1, and up 3. Here we go. Flipped it over the x-axis. I moved it to the right 1. Oops, I didn't do a very good job drawing that. And then I'm going to move it up 3. 1, 2, 3. And we get that final purple graph. It's that final graph that's in purple that we want. If it helps you, like I just drew, you can do each step one by one. Okay? But it's that final purple graph that we want as our final transformation.